Here is a rule so simple a 10-year-old can follow it. Take any positive whole number. If it is even, divide it by 2. If it is odd, multiply it by 3 and add 1. Take whatever answer you get and do the same thing again. Keep going. That is the entire rule. 2 operations, 1 decision. Repeat. Now here is the question that has defeated every mathematician who has touched it for the past 87 years. Does this process always end at 1? Not sometimes, not usually, always, for every possible starting number, no matter how large. The answer appears to be yes. It has been verified by computer for every number up to 295 quintillion. That is a 2 followed by 20 digits. Every single one of them, when you follow the rule long enough, eventually collapses down to 1, but no one has proven it, not even close. Paul Erdős, one of the most prolific mathematicians of the 20th century, looked at this problem and said mathematics is not yet ready for such problems. That was in 1983. Nothing has changed. Start somewhere small. Take the number 6. 6 is even, so divide by 2. 3. 3 is odd, so multiply by 3 and add 1. 10. 10 is even. 5. 5 is odd. 16. 16 is even. 8. 4, 2, 1, 8 steps, 6 to 1 in 8 moves. Try 12, 12, 6, 3, 10, 5, 16, 8, 4, 2, 1, 9 steps, try 19. 19 is odd, 58, even 29, odd 88, even 44, 22, 11, 34, 17, 52, 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, 1, 20, 10, 5, 16, 8, 4, 2, 1, 20 steps. Every number you try comes back. You might go up before you come down, you might bounce around for a while, but so far every number ever tested has found its way to 1, and once it hits 1, it loops forever. 1, 4, 2, 1, 4, 2, 1. Mathematicians call this the drain at the bottom of the universe. Now try 27. 27 is odd, 82, even, 41, odd, 124, 62, 31, 94, 47. You are already past where you started, and the sequence keeps climbing. 142, 71, 214, 107, 322, 161, 484. You are nearly 20 times your starting point, and you have barely begun. The sequence for 27 climbs for a long time. It does not behave like 6 or 12 or 19. It surges upward erratically, sometimes doubling, sometimes tripling, sometimes cutting in half, with no apparent pattern and no sign of turning around. Then, at step 77, it reaches its peak, 9,232. 27 has become 9,232. A number that started small enough to count on your fingers has, under nothing but these 2 simple rules, exploded to more than 340 times its original size. And then it falls. 9,232 becomes 4,616, then 2,308, then 1,154. The sequence plummets in a long, rapid cascade, interrupted by occasional spikes, until finally, at step 111, it reaches 111 steps, a peak of 9,232, from the number 27. If you draw this sequence as a graph, it looks like a mountain range with no predictable terrain. The line rises chaotically, collapses, rises again, then falls for good. Mathematicians call these hailstone sequences because the values rise and fall the way hailstones rise and fall inside a storm cloud, carried up by updrafts, falling, being lifted again, before finally hitting the ground. The name fits. There is something elemental about it, something that feels more like weather than arithmetic. Lothar Collatz was a German mathematician who first wrote down this problem in 1937. He was 24 years old. He did not publish it. He kept it in his notebooks and shared it privately at mathematical conferences over the following years, asking colleagues if they could explain why the sequence always seemed to return to 1. It spread slowly through the mathematical community the way a rumour spreads, passed from person to person, tried by hand, tried on early computers, tried again on faster computers. It collected names. In the United States it was called the Syracuse problem, in England the Hailstone Conjecture. In some papers it was called the Ulam Conjecture, after the Polish mathematician Stanisław Ulam, who became fascinated by it independently. In others it was called the Kakutani Conjecture or the Thwaites Conjecture, after other mathematicians who encountered it and could not leave it alone. Collatz himself lived until 1990. He never solved it. He gave his name to a problem that would outlast him, and so far every mathematician who came after him. When Erdős called it beyond the reach of mathematics, he was not being dramatic, he was being accurate. The problem does not look like other unsolved problems. Most famous open questions in mathematics have some structure that suggests an approach, some framework within which a proof might be constructed, even if no one has found it yet. The Riemann hypothesis is hard, but mathematicians know roughly what tools a proof would use. Fermat's last theorem resisted for 3 centuries, but the direction of a solution had been guessed at for decades before Andrew Wiles found it. The Collatz conjecture does not have that. There is no agreed upon approach. There is no partial result that gets you meaningfully closer. There is no framework that seems to fit. The problem sits outside the edge of what current mathematics can even begin to reach for. Computers have checked every starting number up to 2 raised to the power of 68. That is not a number most people can visualize, so think of it this way. If you started a computation at the birth of the universe and checked 1 billion numbers per second without stopping, you would need to run that computation for more than 9 times the current age of the universe to reach that number. Every single one returns to 1. This is not evidence of a proof. In mathematics, checking cases is not a proof, no matter how many cases you check. There are conjectures in number theory that hold for the first trillion examples and fail at the trillion and first. The history of mathematics has enough of these to make every unproven conjecture suspicious, no matter how much computational evidence supports it. And the Collatz conjecture has a property that makes mathematicians especially uneasy. It does not degrade gracefully. Either it is true for every number, or there exists somewhere in the infinite landscape of whole numbers a starting value that never comes back, a number that bounces forever, never reaching 1, or a number that grows without bound, climbing toward infinity under these 2 simple rules. We have never found such a number. We have no reason to believe one exists, but we cannot rule it out. The conjecture might be false. The counterexample, if one exists, could be somewhere in the vast dark of numbers beyond 2 to the 68th power. We have no way of knowing. What makes the Collatz conjecture so unsettling is not just that it is unsolved. Unsolved problems are common in mathematics. What makes it unsettling is that the rule is so simple. 2 operations, pick a number, follow the rule, and somehow, in the infinite space of all possible whole numbers, we cannot say with certainty what happens. This touches something fundamental about mathematics and computation. In 1936, Alan Turing proved that there is no general algorithm that can determine, for any arbitrary computation, whether it will eventually stop or run forever. The halting problem is undecidable. You cannot write a program that looks at any other program and correctly tells you every time whether it terminates. Some mathematicians believe the Collatz conjecture might be undecidable in a similar sense, not just unproven, unprovable. A statement that is true but lies beyond the reach of any formal system of mathematics. Gödel showed in 1931 that every sufficiently powerful mathematical system contains true statements that cannot be proven within that system. We do not know whether the Collatz conjecture is one of them, but the possibility sits at the edge of the problem like a shadow. There is a broader lesson here. Simple rules do not guarantee simple behavior. The rule for the Collatz sequence is 2 lines. The behavior it produces, the wild ascent of 27 to 9,000 232, the million-step sequences that appear when you try certain large starting numbers, the complete absence of any pattern that would let you predict how long a sequence will run, that behavior is anything but simple. This is not unique to mathematics. Weather systems follow simple physical laws and produce behavior that cannot be predicted beyond a few days. The double pendulum obeys Newtonian mechanics exactly and traces a path that looks completely random. Evolution operates by a small number of rules and produces the entire diversity of life on Earth. Simple rules, iterated long enough, produce outcomes that cannot be derived from those rules by any shortcut. The only way to know what the sequence for a given number does is to run the sequence. The Collatz conjecture asks whether one particular simple rule, applied to any starting number, always terminates. We believe the answer is yes. We have checked more numbers than there are atoms in any conceivable human artifact. Every single one comes back. But belief is not proof. And mathematics is the one discipline where belief, without proof, means nothing at all.